Yeah, thank you very much. Thank you very much for inviting and introducing. So I come from a completely different side, very much from the neuroscience, but I want to show you some implications. So I will show you a lot of empirical data, but I hope can indicate some of the implications for some of the topics we discussed here. And I start with the typical philosopher's question, what is the brain, which usually a scientist would not ask because he's only interested in how does the brain function. But I would say that we really need to think about what is the brain. And that touches upon the question of the model of brain. So what kind of model of brain you presuppose? You see here, some of you may know this very famous movie, Frankenstein. He takes the abnormal brain to create a human. And the basic question really is, and I think much of what neuroscience is very popular in the media these days. By the way, there's a handout for my talks, is really Arthur Schopenhauer in the 19th century said it very nicely. The brain is just a pulpy gray device. I added the gruesome. And how is it possible that some gray, gruesome, pulpy device can at least contribute, so I formulated very carefully here for the philosophers, contribute in generating mental features like self and consciousness. So just a priori, because we had the discussions yesterday, when I speak here of self, I don't mean it in an ontological sense, I mean it in a, at best, phenomenal experiential sense, meaning a sense of self. So don't pin me down on this one. So I start with the model of brain. Obviously, you know that in the history of philosophy, there have been different models of mind, and you will see certain convergences, analogies. The really typical classical and still very much presupposed model of brain is really, it's basically a behavioral cognitive reflex apparatus. That goes back to Charles Sherrington, neurophysiologist, 19th, 20th century, sensory-motor functions, and it has been more or less really taken over also by current cognitive neuroscience. When you look at the imaging experiments, they really presuppose this kind of view. So how does this go? This was a paper 2012, which I published here. And basically, you have a stimulus, an extrinsic stimulus. All of you know this. And that sort of, with that, you stimulate the brain. Maybe you have also control stimulus, let's say in imaging. And what we observe is an activity change, which is called usually stimulus-induced activity. And very important, we associate this stimulus-induced activity sufficiently with the stimulus itself. Meaning the stimulus could be either an external stimulus or also an internal stimulus like the heartbeat inducing some change up there or some other internal stimuli is sufficient for the observed activity change / the stimulus-induced activity. And then, of course, that leaves it unclear where mental features come. So how is it possible that suddenly what the neuroscientists observe as stimulus-induced activity is associated with a sense of self and consciousness? Consciousness here defined again just in a phenomenal sense by phenomenal features like we had the intentionality, I will come back to that, qualia, temporal continuity, stream of consciousness, etc. So that's really, I think, the predominant model of brain in past and current neuroscience. However, on the sidelines, already from the very beginning, Graham Brown, student of Charles Sherrington, observed deep down in the spinal cord some spontaneous activity changes independent of any movement. And that sort of has been picked up by Carl Leschly, psychologist, first part of the 20th century. More recently, Linas and dream research, Schulman on the metabolic side, Panksepp on the behavioral side, and the imaging people among you know Marcus Reckle on the default mode function. So how does this start? Here we really start with an intrinsic activity signified here by these bars. And with that, you approach the stimulus. So what we see as stimulus-induced activity or task-evoked activity is really a mixture between this one, between the intrinsic activity and the stimulus. And you all know this. When you perceive yourself in two different mood states, Either when you're very happy, you say, oh, I'm looking so young, I'm just beautiful, no wrinkles whatsoever. Next morning, you're completely depressed, and you see, oh God, I'm aging considerably. So you see exactly, let's say, the same, forgive me, the same face or stimulus in completely two different ways. And that difference obviously can only come probably from the impact of this spontaneous activity. And my talk will be much about this. So we don't really know much about this spontaneous activity, let alone how it is related to mental features. And that's exactly the central assumption of my talk, that this spontaneous activity is central, indispensable, is a necessary, though non-sufficient condition of mental features. And I show you that with respect to the sense of self. I leave open the question for consciousness, would be a different talk. If you want, we can discuss this. So, and obviously such a model of mind, such a model of brain, is not that far, carries certain analogies to the model of mind suggested by Immanuel Kant, so that I did these analogies. This is a book in German I brought out. And it's, of course, there's some discrepancy. Of course, for a pure Kantian, would probably not follow that, so you have to sort of interpret Kant in a more liberal context. So, what will be my talk about? First, because we talked so much about emotions and quasi-emotions, I want to show you some data, earlier data of ours, where we investigated the relationship between self and emotion / motivation. I will just show you the main thesis here. There's an intrinsic relationship between self and emotion. And that sort of provides further empirical evidence. Then the core part of the talk, really the heart of my talk and of all my thinking these days, is really the link, the intrinsic link between the self, the sense of self, and our brain's spontaneous activity or resting state activity. So there I will show you some surprising findings which very strongly led me shifting from the cognitive reflexive view to a sort of more spontaneous based view of the brain. And then more briefly at the end I want to indicate how this relationship between resting state and self can be traced back to the relationship between the brain and the environment. I show you some data from a recent study of ours here. And then I will conclude. Throughout the talk, I will mix some empirical data. I will not go too much into detail of that. If you want to have more detail, obviously you can ask me. So I will basically just summarize the main message through some slides and then more focus on the conceptual implications which are interspersed with slides. So that's basically the main talk, and self is everywhere, so we do also the research in China, transcultural difference. So let me start with the first part, the relationship between self and emotions. You heard already yesterday there were a lot of correlations. I think you reported that between self-relatedness and emotional intensity, and we heard it today in the talk on autism as well. So this is already a ground, and here I want to provide you further support for that view. Let's start with the self. Some of you may know this. This is a paper we published in 2006 here, where we did a meta-analysis of all studies on self-relatedness. So in an operational way, you compare a stimulus which is highly personally relevant for you, like a beautiful a picture from Paris, and you compare it with a picture which probably bears no self-relatedness at all, meaning snowstorm in Ottawa. So if I present you with that combination, you will show a lot of activity in these regions of the brain. Basically, when you slide your brain in the half, this is what you see, the so-called cortical midline structures. We coined this term, and this is the core region of what has been indicated today also of the default mode function. So, and amazingly, I indicated that in your talk this morning, that the autobiographical memory is included here, also really recruits the cortical midline structures. And that's amazing across different domains, whether you present emotions, face, memory, motor, social, spatial, verbal. When you present personal versus non-personal relevant, you see the recruitment of these regions. So that really has contributed a lot to theorizing about the function of these regions. So now the question is, what does it mean in psychological terms? This is and/mental terms. This is the main focus of this talk. We have another line of research where we really focus on the physiological underpinnings, the kind of physiological mechanisms which go hand in hand. So, the first thing, some emotion studies. We presented emotional pictures here, and very important, we particularly focus on this one, pure perception. There was no mouse click, the judgment came here, but we focused on this because we just wanted to have pure perception. No motor related, no cognitive related activity. The little mouse click makes a huge difference for the poor brain. So why on perception? I just wanted to focus on my idea was coming from phenomenology, just on experience. So then subjects had to evaluate emotional intensity, emotional valence, and the degree of self-relatedness of these pictures. And then we correlated this, and what you can see here in these pictures is all those regions during the emotional perception which correlated with the degree of self-relatedness. And you see again, you see a lot of subcortical regions, so deep down in the brain here, and you also see cortical regions. So that was already a hint, sort of the subcortical regions which have been implicated in emotions. And that's amazing thing, that even already in the subcortical regions, you see a relationship to self-relatedness. Because usually the subcortical regions are just usually implicit motor processing, physiological body processing, but not presumably higher order function like self-relatedness. So, and then we plotted this is a complicated graph, but what we plotted that the same regions had an involvement of both self and emotion. So when you just make a categorical comparison, you see the involvement both. But then you do a parametric plotting according to the subjectively perceived degree of self-relatedness or emotional intensity, and then you see different kinds of relationships. And then in a way that's very economic, because the brain, emotional and self-relatedness are processed in the same regions, but maybe in different ways. And that's how we can then distinguish between high and low self-related emotions. Some other regions, like the amygdala, by the way, showed a similar relationship where you could not distinguish between the two. So that just gives you a model that there's a complicated, sophisticated relationship. On the one hand, they seem to overlap. On the other hand, they seem to dissociate from each other in the way they function. And you see already these were many subcortical regions, and again, particular subcortical midline regions, which you usually would subsume under the concept, some of you probably have heard it, the limbic system. Limbic system for the basic emotions, and here apparently also association with the self. So this and some other studies let us assume that maybe the self needs to be linked to a subcortical cortical midline system, which anatomically makes sense because evolutionary, the cortical midline structures result an extension of the subcortical limbic system. Yeah. So, further evidence for the involvement of the self, we here conducted study on reward. Reward is a basic function, so let's say when you get one of these nice cakes here in Paris, or you have to write the paper and then you get a cake, so this is the reward. And here we tested it by gambling. Certain people had to gamble on the stimuli, had to bet, and the same stimuli subjects had to evaluate as personally relevant. And the main idea was here, looking whether in reward regions of the brain, we also have activity during personal versus non-personal relevance or self-relatedness. And this is indeed the case. So here you can see this is a classical reward regions, nucleus accumbens, ventral striatum, very typical. And you see when you win, lose, you have a good differentiation. And interestingly so also, when you perceive the same stimuli as self-high or self-low, you also have a distinction. So that was quite a surprise that apparently self-relatedness is closely, intimately related with reward. That of course raises the question, are they the same? our reward is self nothing but reward? That's of course another question. We did subsequent studies also in patient studies, pathological gamblers, where we could show a dissociation between self and reward. So that means they are not identical. Here, I'll show you more regions. Here, even a region for the experts among you as deep as the ventral tegmental area shows a strong self-non-self differentiation and win and lose. So, what do these findings tell us? Apparently, again, like in emotions, the typical reward system, this is a typical reward system, seem to mediate both self and reward. And the question is, are they really the same or not? As I said, we conducted subsequent studies. So now then, of course, the question is, and you remember my questions throughout yesterday, who drives whom? Is it the emotions driving the self, or the cognitions driving the self, or is it the self driving the emotions? This is empirically very important to understand the mechanism and the psychological relationship. And it is also, for me, philosophically very important because it implicates different kinds of concepts of self. And I will come back to that. So this now leads me to the second talk, sorry. See, my counting is not perfect. So to the second part of my talk, to the relationship between the resting state or the spontaneous activity and the self. And again, you remember this picture, I showed this, and very amazing, and these regions are part of the default mode network. And the default mode network is a set of regions, these are really the cortical midline structures, which show very high activity levels and metabolic levels in the resting state, meaning during the absence of specific stimulus. Resting state is a very paradoxical term. Every philosopher is completely justified to say this is illogical, because if the brain were at rest, the brain would be dead. So there is never rest in the brain. So the resting state is a purely operational term. It's for the imager who said you scan the patients during eyes closed. But it doesn't mean that there's rest. There's actually a lot going on in the brain, and spatial temporal dynamics, and I will come back to that. So, and you see, so very early on, you saw, wow, there's a similarity between this default mode network, which shows high resting state activity when compared to other regions. The whole brain shows a high level of spontaneous activity, but the spontaneous activity here shows certain special features, like it is particular strong metabolic demands, and extreme variable. So it changes much more, let's say, than regions in the sensory cortex in resting state. And it also shows very strong infra-slow frequency fluctuations, meaning it has fluctuations in very slow ranges which are particularly strong in these regions. So meaning it has very long cycle durations. And these may be optimal for integrating stimuli. So, and then and that of course you see, so there's an overlap. This seems to be at least this set of regions seems to be implicated in both high level of spontaneous activity and self. So that of course raises the question, what is their relationship? And indeed, some findings by others and ourselves indicated that there might be an overlap, meaning that in these regions, you do not have much activity change from the resting state when compared during self-related stimuli. So this is a very paradoxical thing, because you would expect if you see a picture from Paris, your brain just gets crazy. It lights up, it shows strong activity changes. Whereas when you see the picture from Ottawa, -40 snowstorm, now you know why I'm here, then nothing lights up. But it seems to be exactly the opposite. That's what the findings suggest. That when you see the picture from Paris, your brain remains in its default mode and doesn't change much. meaning your brain likes Paris. But when you see the Ottawa picture, your brain changes, in particular what we call deactivate. It lowers activity in these regions. So there seems to be, and this is a meta-analysis, what we did in my group, of an overlap between self-related studies and resting state studies. This is a default mode network, and here's the overlap, the typical default mode network regions, and really an overlap between self-related activity and default mode network. So that overlap, we confirmed this form further. We did a single unit recording studies in patients with depression who receive deep brain stimulation. And what we could show, and we presented them their own name versus another person's name. This was a control region. This is subthalamic nucleus, and Parkinson's deep down in the subcortical regions. Here you can see when you hear the own name, you have an increase in firing rates, whereas in response to the other name, you don't. Here you see this too. In contrast, when you have a typical default mode region, this is subgenual cingulate cortex, you don't have an increase in the firing rate during self here. So meaning, even on the cellular level, you seem to have an overlap between resting state and self-related activity. So ultimately, if you take the perspective of the spontaneous activity, it makes you think there must be a special way how the self-stimuli interact with your spontaneous activity. Because they don't induce activity change, but nevertheless you perceive them. So there must be a special interaction, and that is really a new topic, because usually neuroscientists thought you have your, even if you acknowledge the spontaneous activity, the stimulus-induced activity is just superseded. It's just put on top of it. Yeah? So like here, I'm just a little bit higher than the ground floor. Apparently the brain, there seems to be a, so this would be a pure addition or additive interaction. It's just put on top of it. But we showed in the paper just published just a couple of months ago in cerebral cortex, that apparently there is non-additive interaction, meaning the resting state can give a boost, can attenuate, or increase the activity which the stimulus can induce in the brain. Meaning, your resting state is very active. So when you observe me now, your resting state is very active and either attenuates or strengthens the kind of stimulus so that you perceive it properly. And probably according to the degree of self-relatedness my talk has. So if you don't care about what I'm talking, probably your resting state says, I don't need this Northoff, I just attenuate his activity so then there's not so much stimulus-induced activity so that I don't perceive him and I can pursue my own thoughts. He's wrong anyway. Yeah. If in contrast, wow, this is crazy but nevertheless interesting, maybe it makes it strong. And the question of course, how do these mechanisms work? Some of this we address in this paper. I cannot go into that. So, what is clear, this is a nice picture from Italy, from Bologna, Via della Brena. So there seems to be a lot of convergence between the brain, the resting state in the brain, and the self. And that by itself, for me, having also a philosophical background, is quite an amazing thing. Because if that is really true, it has, at least for me, major implications. So, this leads to the following testable hypothesis. So, do self and spontaneous activity just use the same regions, but on independent ground? You can speak the same language, but you nevertheless don't need to talk to each other. So they're completely independent, they just use the same, let's say, the same room in the brain. Or, so that would be a rest, what I call rest-self overlap. So these regions, they use the same regions, but have different forms of, the related activity is different. Alternatively, you might say maybe there's some information about the self encoded in your resting state. If that is so, then resting state must be identical with self-related activity. Of course, I know that there are many other options here. That would be an interesting case also to discuss in philosophy of science. So, So now, of course, the question is, how can you address this? And I show you now 2 studies. This is really one of our main foci now, to see which one holds. First study. So this is a study where we combined EEG and spectroscopy. I leave out the spectroscopy part, it's not that important, but it's this one. So what we did here, so let me just show you the paradigm. So we presented emotional stimuli here, typical EAPS pictures, emotional pictures, and subjects afterwards had to evaluate them whether they were high self and low self. And then we grouped our trials in EEG according to the high self and low self and looked what happened prior to the stimulus, pre-stimulus activity. You may remember I wanted to know the intertrial intervals. You see we have relatively long here. If your intertrial interval is, let's say, about 15 to 16 seconds, which I doubt it is because the cognitive people don't care, then one could do some very interesting analysis. And I bet that your autism patients show altered pre-stimulus activity. Yeah? Particularly in those stimuli which they are supposed to associate with high self-relatedness. Yeah? And that maybe your relationship between self-relatedness and emotional intensity, which you showed, is predicted by the pre-stimulus activity. So, and then we did EEG recording and we also did spectroscopy for glutamate. So here I show you the event-related potential. You see a difference between high self and low self items, purely subjectively perceived. Yeah? So you see a difference here. And now the important thing, so I show you here is the pre-stimulus difference, and you see here a lot of power, particularly in the alpha band, as we call it. And here, this is high self, this is low self, not much power. This is very interesting because the alpha is basically like a gating mechanism. It's like a door. If the stimulus wants to enter the brain, it needs to lower the alpha, meaning it needs to open the door. If it does not lower the alpha, it will not be properly processed. And of course, the degree of your alpha, meaning how tight the door is closed, depends on the features of the resting state. Yeah? So that's a predisposition. And for instance, when you open your eyes, you have the typical, when you get a lot of visual input, you decrease your alpha, meaning the door is open and the visual input can come in. Same here, that predicts self-relatedness. It's very interesting. Further, I don't want to show this so much, it also correlated this alpha increase with glutamate, which is the main excitatory transmitter. So what does this lead to? For a tentative model, basis model, which I like to call the basis model, it probably suggests that there is a rest self-containment, so that your pre-stimulus activity predicts your level of subsequent, whether you perceive it as high or low self-related. This is only possible when there's some information about self-relatedness encoded in your resting state. And we have another paper in press which shows exactly this, a similar thing. And that is very important. So this is a very crucial graph, and I will come back to that later. So with this self-related or self-specificity encoded in yet unclear way in your spontaneous activity, you approach the different kinds of functions. Like, so then you have a stimulus which might be emotional, or you get into your quasi-emotional mode. I will come back to that. You do your perceptions, you have your actions, you have your cognitive social functions. Remember, and also, like for instance, memory would be here, that maybe I raise the question, who drives whom? After these findings, I would argue it is the self-relatedness which drives your memory, and if they merge well, this is what you call autobiographical memory. So, like the same way attention, 10 years ago, I could have never said that self drives attention, because attention was always considered primary. But nowadays, maybe these findings really suggest that maybe your degree of self-specificity drives the degree to which your attentional functions are recruited. So in conceptual terms, this is sort of what I like to call a neural predisposition. And you might have heard the term of not neural predisposition, but emotional presuppositions by Witzak. So I liked it very much. So the degree to which your resting state might be involved, that might correlate with the degree of quasi-emotions. So remember, you had these very nice passages. It's a quasi-emoting, and then in the next slide you had emotional presuppositions, I think. And I would argue this might be this. So, of course, I don't present empirical evidence because you would need to show that emotional intensity is predicted by your pre-stimulus resting state. But I bet that could be shown. Okay. That, of course, raises the question, how is the self or self-relatedness encoded into the brain's spontaneous activity? So, and of course, you see already the answer is a certain temporal structure. Our brain is a highly dynamic organ. Continuous frequency fluctuations continuously change. It's a dynamic change. If the brain doesn't change, you lose consciousness and you become vegetative state, and then you become brain dead. We have several investigations into that. So if it doesn't change, you have plenty of frequency fluctuations in different frequency ranges. And these frequencies stand in a particular relation. So what did we hear? So here we, spontaneous activity, recorded that, and we gave subjects a self-consciousness scale, which is well validated, and it has 3 subdimensions: private, public, social self-consciousness. And so what we did here, you can see here, I know this is difficult to understand, so you have different kinds of frequency ranges, and each frequency range has a certain power, strong. And interestingly, the lower the frequency range, the higher the power. So, and ultimately this amounts to what we call, what can be called, measured as a power law exponent. Basically, it's your relationship between power and frequency, and then you do a log-log transform, and then you end up with a power law exponent. Interestingly, the power law exponent, meaning the relationship between lower and higher frequencies, is an abundant feature in nature. So this power law distribution is abundant in nature. Apparently, is also the case in the brain's spontaneous activity. But, and this is the interesting thing, so here I show you the typical log, here the frequency, the power spectrum. You see the lower the frequency, the higher the power. Each line is one subject. The higher the power, the lower the frequency fluctuation, the higher the power. The higher the frequency, the lower the power. So this is typical holds, but there's a lot of inter-individual differences. And these inter-individual differences, particularly here in this region, and you have seen this region before medial prefrontal cortex, predicted the degree of private self-consciousness. So this is pure resting state, a relationship between lower and higher frequencies, your temporal structure, an index of a temporal structure, and that predicted your degree of private self-consciousness. Meaning, the higher your degree of power law exponent, the higher your private self-consciousness. And interestingly, that only holds for the private dimension, not for the public, nor for the social, and also only for this anterior region. Okay, now I have to speed up. So that's sort of the first evidence that really apparently there's a temporal structure and also a spatial structure, which I don't go into here, which might mediate some of the encoding of these mental features. And of course, philosophically, I like to use the form of the concept of form, which was put earlier in your talk on the cinema. So I find it very interesting, the different concepts of form. And of course, I'm too much of a Kantian, good old German Kantian. So for me, I conceive the spatial temporal, the brain's spontaneous activity in terms of a spatial temporal structure as form, and this is very important. And we are just at the beginning. This is a necessary condition for the possible realization of mental features. So that's basically the way I would formulate it. So it's a very different view of the brain than a cognitive content-based view. I start exactly from the other way, and I come in terms of spatial temporal features. That's why I asked you this morning, how do these patients experience time and space? When I approach my schizophrenic and depressed patients, that's what I'm asking them, because that gives me much more insight about their brain and also how they experience, and that in turn shapes their cognitive content. Okay, so I skip that one. This is very relevant. So I would consider psychotic symptoms as spatial-temporal symptoms, not as cognitive symptoms. So there are spatial-temporal symptoms of the resting state. I did this here in depression. We have a paper in revision on schizophrenia. Autism would be another very interesting example for that. And ultimately, many psychiatric disorders have been conceived as basic disturbances of the self, not only schizophrenia, also depression. Autism, it's very clear. So I think that really provides also new insight into these disorders. So, yeah, so if you have, so I think philosophically, I can only indicate this very briefly here. The typical view, also Kant, is a higher order cognitive view of the self, or of the ego, or whatever you want to call it. So please forgive me if you don't agree with the term. And that has been really transported also into philosophy. Bennett and Hacker were really right that current neuroscience is very Cartesian. So, and that so has been sort of, then you have a cognitive self, a meta-representation, specific regions of the self, and so on and so on. That really reflects a Cartesian, a neural Cartesianism, if you want to say so. I think the data speak a different language. You start with your spontaneous activity. In yet not fully clear ways, there's some self-specificity encoded, and that in turn modulates all the other functions. And when I saw your passage from Wittaszek, where he thought you have a quasi-emoting, and then the next slide was emotional presuppositions. Of course, you can imagine that's exactly what I would locate here. Your emotional presupposition. And the stronger this is involved, when compared relative to the external stimuli, the stronger the quasi-emotion part in your affective emotion. So it's a balance between internal and external, between self-related, between this one, and external. The stronger this one is, the stronger probably the quasi-emoting part in your actual emotions are. So it's a balance. We did the same, would be very interesting to study this. We did the same for decision making, internally versus externally guided decision making. Yeah? So it's really a balance. It's not either internal or external. And this balance decides upon the balance between quasi and real in, as you would say, or in the motion between internal, external, or self-related or environmental driven. Okay, so some of these conceptual implications I discuss in this book, Minding the Brain, where I try to make fruitful, where I discuss a model of brain, and I discuss the implications of some of the findings for philosophical concepts. So, this is from Milano. You see, I like Italy. I love Italy. So, the self bars, you see them everywhere. So, I come to the last 4 or 5 slides. And so, the question is, where on earth is this relationship coming from? Kantian would probably might say maybe it's an innate relationship. You know that in the concept of Kant is the innate features of the mind. Then there has been an evolutionary approach to Kant by a German, I can't remember his, Gerhard Vollmer, very interesting. So where is this coming from? This is exactly the question. So this is my argument. So there have been some indications that the functional connectivity in the resting state has been associated with early traumatic life events. So we dwelt on that, and one of my postdocs from Scotland, Neil, did a very interesting study. It's a crazy study. He combined all kinds of imaging modalities, and I want to save you that. But I want to show you the main thing. So we investigated adult people and scanned their resting state and also their biochemistry. And we also gave them a particular questionnaire for early childhood traumatic experiences. And what is important, what this childhood questionnaire, CTQ, childhood traumatic questionnaire, measures is not the objective life event. That's very important. But it is the life events as they are perceived. So what you see is the way they perceive the life event. Maybe the same life event might be perceived as traumatic and as non-traumatic by another person. So, and what we observed is very interesting. So here we applied yet another measure of spatial-temporal structure, meaning entropy. That's the degree of similarity or dissimilarity of spatial-temporal patterns across time. So if they change a lot, you have a high degree of entropy, and your spatial-temporal system is rather dynamic / if not unstable. So, and here we observed that the higher your degree of entropy in the resting state, again here in this region, the higher your degree of early childhood trauma. So this was in the adult state, this was in early childhood. And then we observed an analogous relation with the level of glutamate. Glutamate is the main energetic metabolite, gives energy to the brain, and excitation, part of the excitation inhibition balance. You see the opposite. The more glutamate you have, the less early childhood trauma. So this is, of course, the very beginning, but it tells you then, this is, I don't want to go into this, just indicates, so here we observe that the resting state changes in their relationship to the early childhood also impacted aversion-induced, stimulus-induced activity. So you really have sort of a threefold level from the interaction between world and brain to the resting state to the task-evoked activity. So, and of course, you can say this might be some kind of memory, you might say. But it's probably not the kind of memory you were talking about. So I would probably rather talk, maybe there's some sort of spatial-temporal memory. It's maybe the kind of memory, I'm never sure in his case about Henri Bergson is talking about. But I'm never sure because I'm not sure whether I fully understand it. So I would probably, it's a precognitive, spatial-temporalized memory of your early life events or of your relation to the world, because these are the life events as you perceive them. It is not the objective life events. It's very important. Okay, so coming to the second to last slide, what does it mean? So I want to sketch some implications. So first, sort of as a model, and I think this is very important for subsequent philosophical considerations and discussion. So first you have this interaction between the worlds, these are, let's say, the life events and your brain. And I showed this arrow that the life events are somewhat encoded in your resting state. I didn't really show this way because that this is an active process of the brain. And there are empirical studies, which I cannot go into it. This is very active. So the brain itself, if you want to say so, provides an input in its interaction to what it receives from the world. And that's why you encode in your brain the life events as you perceive them, not as they are real. Otherwise, the brain would be just an information processing device, which I strongly object. It's not. It's a much more basic, it's a spatial-temporal dynamic device which tries to align and cope itself and tries to nest itself within its respective environmental context. Psychiatric disorders are a very nice example of that. And that in turn, here I like to speak of a world-self, or if I go deeper, world-brain relation. And I would argue that this is probably, if you want to have a correlate of that on the experiential level, might be the phenomenal self. So this is the self which is always with you, stronger, less stronger, but it's always with you. You cannot throw it out. It's always with you, somewhere in the background. Sometimes it depends on the internal, external balance. And that in turn strongly impacts how you, for instance, perceive this picture. This is from Amsterdam Airport. And then how yourself impacts the world. So this is where you have perception, emotion, and cognition. And considering the topic of this conference, I would put forward the very tentative, obviously, it depends on how strong this world-self or world-brain relation is. And that in turn is a predisposition, it's just a predisposition / a necessary condition of the possible relation between reality and between real and quasi or real and fictive elements in your subsequent perception and emotion. So you have also a quasi perception, schizophrenic patients with auditory hallucinations. They have a lot of quasi perception, and healthy subjects can have auditory hallucinations too. Same with the cognitions, emotions. We discussed it extensively. So I would argue probably that is predisposed by the balance between these two. So, last slide. I think in neuroscience, I think we are really just at the beginning of understanding the brain, and maybe, at least as you could see, I claim for a shift in the model of brain from a cognitive model to a spatial temporal and ecological or neuroecological model. And that, of course, opens also the door for seeking for analogies in philosophy. And you can learn a lot from the models of mind in different philosophers and see where they went wrong, where there were problems, and learn for the brain. And then ultimately develop a theory of consciousness, what I try to do in this way, or that you can really also better understand psychiatric patients and learn from them how the brain functions, what I do in this book, which just came out last week. Thank you very much.